Hello, my name is Gogoll from the University of Bonn. In this talk I will introduce you to an effective approach to unsupervised domain adaptation for plant segmentation systems in agriculture. Our approach helps to adapt existing classification systems to new environments, different value crops and other farm robots. In conventional farming, tractors apply large amounts of agrochemicals uniformly across the whole field, which has negative impact on the environment. However, in times of increasing food demand and global climate change, the present arable land has to be cultivated more efficiently. Farming robots have the potential to reduce those negative impacts by a targeted treatment through actuators like selective sprayers, lasers or mechanical tools like you can see on the bottom right image. On this image you can see how the robot perceives the field. Vision-based classification systems form the basis for such weed control interventions. They reliably distinguish between crops, weeds and soil, mostly using fully convolutional neural networks for semantic segmentation. These classification systems typically achieve a performance around 90% or more when the trained classifiers are deployed in similar field conditions. We call those similar environments the source domain. However, the performance of a classifier which has been trained in the source domain suffers substantially when being deployed in new field conditions. We call those new environments the target domain. The domain shift is affected by a different visual appearance, induced by different weed types, growth stages of the plants, soil conditions and illuminations. In this paper, we aim at bridging the performance gap in visual crop and weed classification through transferring the visual classifier to the targeted domain without the need for an additional labeling effort. We target unsupervised domain adaptation towards an approach that enables us to train an FCN with suitable performance on the target domain while exporting labels only from the source domain. We propose an unsupervised domain adaptation approach that can adapt existing segmentation systems for crop weed classification to new domains, still yielding a high classification performance. We exploit unpaired image sets from a source domain and target domain, as well as labels only from the source domain. Our approach consists of two domain-specific FCNs for semantic segmentation and a domain adaptation module. We train the source FCN in a supervised way using RGB images and labels from the source domain. We cannot act in the same way in the target domain since we are missing target labels. Now, how do we train the Target-FCN? We make use of the domain adaptation module to translate the source image towards the target domain. Within the domain adaptation module, we perform a style transfer. In particular, we transfer images from the source domain into the style of the target domain. We finally train the Target-FCN in a supervised manner using the translated images in the style of the target domain alongside with copied labels from the source domain. The source FCN and the target FCN share the same network architecture. They take RGB images as input and output respective semantic segmentation maps, encoding a pixel-wise classification into crop, weed and soil. The network architecture incorporates 5 fully convolutional building blocks based in the UNet architecture. Our domain adaptation approach is based on CycleGANs, which is an image-to-image translation technique introduced by Zhu et al. The domain adaptation approach learns the mapping between the source and the target domain in an unsupervised manner. We achieve this by jointly training two generator networks G and F using unpaired source and target images and pixel-wise source labels. They perform the translation of images into the style of the opposite domain. During the training of the GAN, their respective discriminators aim to distinguish between real and generated images. Technically, the discriminator networks can be seen as dynamically updated loss functions that train the generators to create fake images that are close to real images. At the same time, the generators try to deceive the discriminators for recognizing whether the image is real or generated. In a forward pass, we translate the images between the domains within 2 cycles. The generator G translates the real image into the style of the target domain. Then generator F translates the translated image back into the style of the source domain. Following the implementation of CycleGAN, we enforce a cycle consistency constraint through an L1 loss and apply an adversarial loss as introduced for GANs by Goodfellow et al. This pushes the generators to create fake images that look similar to real images from the opposite domain. The problem with CycleGANs is that they give no guarantee to preserve the semantic information for the translated images. However, semantic consistency during translation is key to train the Target-FCN. We propose additional semantic consistency constraints for training the domain adaptation. We include the 2 domain-specific FCNs into the training process and compute additional semantic losses that finally add to the overall training objective. The key idea is that all images of one cycle should share the same semantic information and will be classified in the same way before and after translation. I refer to our paper for more details on the semantic losses. This example shows that the additional semantic losses forces the generators to produce semantically consistent images in the opposite domain. We carry out experiments on a wide range of real-world datasets showing different types of crops and weeds. The image sets were acquired using farm robots as well as UAVs with different camera setups each. The experiments are designed to support our claim of providing solid performance for crop weed classification in new domains without requiring extra target label effort. Additionally, we claim that our approach outperforms CycleGAN on the target domain and can transfer a classifier between different fields, different crops, and different camera setups. The first experiment shows the domain transfer between different field environments. In the upper row, you can see that our approach reliably generates images in the style of the target domain, whereas the CycleGAN baseline generator misses details in the texture as well as the semantic information for small vegetation objects. As the second row indicates, this in turn leads to a weaker crop weed classification in the target domain. The second experiment shows the domain transfer between different crops, in this case sugar beet and sunflower. The qualitative results illustrate that our approach performs better for those small vegetation objects since the semantic information is kept during translation. The last experiment shows the domain transfer between different camera setups. Noteworthy is the low performance obtained by CycleGAN. It cannot preserve the semantic information for small plants during the image translation. Therefore, CycleGAN maps pixels from the actual soil class to vegetation pixels in the target domain. The wrong translation prevents a correct adjustment of the Target-FCN. The quantitative results show that the vanilla baseline fails on all target domains, indicating the need for any kind of domain adaptation methods. Moreover, our approach substantially outperforms CycleGANs. This is reasoned by the fact that CycleGANs cannot preserve the semantic information, especially for small plants during the image translation. In this talk, I presented an unsupervised domain adaptation approach to the problem of pixel-wise crop weed classification. You saw that our approach enables to retrain an FCN that achieves a solid performance in changing domains, such as new field environments, different crops and different sensors, while exploiting labeled data only from a source domain. Our extensive evaluation demonstrates that we outperform CycleGANs in changing domains and substantially improve the generalization capabilities of crop weed classification systems. Our approach learns a mapping between unpaired images from the source and target domain by exploiting cycle as well as semantic consistency constraints. With this, I thank you for your attention.